Greetings, it's Paul Bamberg with the introductory video for Class 9 of Math 117. We're going to be talking only about simple random variables today as an introduction to defining more formally the concept of expectation. So let's think about how we can extend the general concept of measure. Examples of measure from everyday life are length, area, and volume. And I think most people will agree that if you say the closed interval from 0 to 1 in the real numbers has a length of 1, then any subinterval that runs from a to b has a length b minus a. And since ancient times, mathematicians have been trying to figure out the total length of a geometric figure that's made up of a finite number of such intervals, and they do this by adding up the lengths. In particular, Archimedes, who was active in Sicily in the 3rd century BC, and Francois Viet, who was in Renaissance France, both invented ingenious methods for calculating pi by approximating the perimeter of a circle as the limit of the total length of a finite polygon. Much later, Burrell had almost the right idea. His idea was you can define the measure of a Burrell set by adding up the lengths of disjoint intervals. There might be infinitely many such disjoint intervals, but as long as they're disjoint, there can only be countably many of them. And this idea turned out to have an extremely subtle flaw. Namely, there are Burrell sets that, although they have measure 0, they still have subsets that are not Burrell sets. You know one example of such a set, a Vitali set. And so, although these sets have 0 measure, they're not measurable because they contain a non-measurable subset. It was Henri Lebesgue who fixed this problem by saying that the measure of a set just doesn't change if we add or remove a set of measure 0. And you'll encounter this idea in spades when we discuss Lebesgue integrals. So let's think about how to define expectation. We've got a probability space, that is, we have a sample space, we have a sigma field, fancy F, and we have a probability measure, P. And let's suppose you're playing a game where if event A occurs when an experiment's carried out, you win $1. In that case, the indicator function for event A is a random variable on the probability space. It's a function that equals 1 for event A and 0 for the complement of event A. And any reasonable gambler would say the expectation of this random variable is equal to the probability that event A occurs. This is simply saying if you're betting on an event that has 1 chance in 4 of happening, your expected winnings will be a fourth of $1. And you can justify this by saying if you repeat the experiment a large number of times, you expect your winnings to be very close to the number of times you play times the probability that event A will come up. So we've got to start. We'll define the expectation of the indicator function for A by saying the expectation of 1 sub A is the probability of A. And all we want to do today is to try to extend this result to the case of a so-called simple random variable. That's just a finite linear combination of indicator functions. And you say, what could be easier? Let's just add them up. Well, it is easy. We'll do it. But then we will be very successful later on in approximating other random variables by sequences of simple random variables. You'll recall, I hope, that if we have a measurable function whose image is finite. Deneen uses the term range, but I really don't like to use range because lots of folks like to use range as a synonym for codomain rather than image. So the image is finite. That is, there are only a finite number of values that can be achieved by this function. And we've already learned to write this as a linear combination of indicator functions. If you think of the example of a dartboard, the various events are the inverse images of the scores you could get. For example, if it's possible to score 10 by landing in some region, the region where the score is 10 is an event A sub I, a subset of the set of points on the dartboard. All the C sub i's are distinct from one another because we're just enumerating the different scores. So we might have two different regions where the score is 10, but we lump those two events together and have just one entry for the score of 10. These are disjoint events, and they partition the sample space. And so we can say the expectation of this random variable is simply equal to the sum of the score C sub I times the probability that the dart lands where we get that score. And in fact, we can push this quite a bit further. We can say the result still works if the events A sub I are any finite collection of disjoint measurable subsets. In that case, C sub I and C sub j might be equal for different subsets. If you're thinking of the example of a dartboard, that just means we could treat separately two regions on the dartboard, both of which led to a score of 10. Now there's another way of doing this, which is very popular and that's so obvious that many people take it as the definition of expectation. Suppose we've got a finite sample space. Then a perfectly good sigma field is the power set of the sample space, 2 to the omega. And in that case, any random variable is going to be simple because it can have at most n different values. So now any point in the sample space is in the sigma field. There are only finitely many of these, and the most general event in the sigma field just consists of some collection of points omega. So it's consistent with our previous definition just to say we will use the indicator function for each singleton set, each set consisting of a single point in the sample space, and then in accordance with our previous formula, we just run over these sets. We run through the sample space, multiplying the probability that event omega occurs by the payoff, the value of the random variable x, when that occurs. And we get the same result as we would by partitioning the sample space according to the different possible values of the random variable. This has a name. It's called the law of the unconscious statistician, and I think the word unconscious was probably introduced because many people write down the formula in the middle, either believing that it's the definition or that it's so obvious that it requires no comment. But in fact, the definition is the formula on the right. That's going to turn into a Lebesgue integral, while the formula in the middle, when we try to generalize it, is going to turn into a Riemann integral. Because Lebesgue integrals are nice theoretically but difficult to evaluate, the Riemann integral formula in the middle is often the one you want to use for computation. Now let's consider the possibility that the sample space might not even be finite. It's still possible for the random variable to be simple if x can assume only one out of a finite set of values, and we again have a nice formula for expectation. For any value, x sub I, we choose some representative point, omega sub I, on which the random variable has the value x, and we can again do a finite sum over scores. We just take the score for the representative point times the probability that that score occurs. Now there are lots of properties of expectation, most of which, if you're thinking of expectation from the point of view of a gambler, are fairly obvious. These are, in fact, all provable theorems, and you'll get to work on proving some of them in the second set of group exercises when you come to class. Here they are. You'll agree with me, they're pretty obvious. The expectation of the sum or difference of random variables is the sum or difference of the expectations. For independent random variables, the expectation of the product is equal to the product of the expectations. Multiply a random variable by a constant c, you do the same thing to its expectation. If a random variable is always positive, so is its expectation. If random variable x is always larger than random variable y, the expectation of x exceeds the expectation of y. And if for every event in your sigma field, the absolute value of the random variable x is less than some quantity m, then if you restrict yourself to considering the indicator function for a, the expectation of x restricted to a cannot exceed the maximum value m times the probability that event a occurs. Now I'm going to introduce some bizarre notation. Bizarre because we're doing finite sums at the moment, but we're going to write the expectation of a random variable x as the integral over a sample space of the random variable x dp. This will be very nice notation later on when we consider Lebesgue integrals, but it makes sense even now. Let's think about what it means for simple random variables. We've got a finite partition of the sample space into measurable sets, and on each of these measurable sets, the random variable has a certain constant value, x sub I. There may be many points in a sub I, but we can always ask for a representative point characterized by the property that when we apply the random variable x to it, we get the value little x sub I. If you're thinking of dartboards, omega sub I is just some arbitrarily chosen point in the region of the dartboard which leads to a score x sub I. So in that case, we can write x as a linear combination of indicator functions. We already have a formula for the expectation, namely the value of the random variable on the representative point times the probability of the event to which that representative point corresponds. But we can write this as an integral in our new notation. Again, the expression on the right looks like a Lebesgue integral. The expression in the middle, on the other hand, looks like a Riemann sum, doesn't it? What do you do when you have a Riemann sum? Well, you'll take some little subdivision of an interval on the real line, and on that subdivision you'll choose some representative point in the subdivision, look at the function value, and say the contribution to the Riemann sum is the value at the representative point multiplied by the length of the interval. If you're doing this in 2 dimensions, you say its representative point value times the area. If you're doing it in 3 dimensions, you can say, let's break space up into lots of little cubes, and for each cube, the contribution is the function value somewhere inside the cube times the volume of the cube. We're doing the same thing here, except instead of using length, area, or volume as our measure, we're using probability. Now let me finish by introducing an important limit theorem that's going to turn out to be very important later on, even though in this case it's kind of trivial. Suppose we've got an increasing sequence of simple random variables. The way I like to think of this is there's one of these random variables for each day, and the random variable is a payoff function that gets progressively more and more generous. You might, for example, discover that at your favorite local pub, every time you go back to the pub, the payoff for regions in the dartboard has gone up. In that case, if you think about the payoff for a specific point on the dartboard, those values are going to form an increasing sequence of real numbers. Now let's imagine we have two different pubs with identical dartboards but different payoff schemes. However, the payoff schemes both approach the same limiting value. In that case, we have two sequences of increasing random variables, x sub n and y sub n, and the limits are the same for both. What are we going to prove? We're going to prove that the limit of the expectation for x sub n is the same as the limit of the expectation for y sub n. How could it be otherwise, you might well ask, but this is going to turn out to be a very important thing to prove in the case where we're considering random variables that are not necessarily simple. The full proof is in Deneen. We'll look at it more carefully in class, but let me outline the proof strategy here to finish up. So, we're going to fix the value of m and look carefully at the random variable y sub m. That's the payoff scheme in the second pub on day m. And let's think about all the possible functions in the sequence capital X sub n. For each of those, there are two subsets into which we can partition the sample space. We can say there are going to be some values of omega for which the payoff function on day n is greater than y sub m on that day, which is, y sub m, which is on a specific day m, or at least close to that in the sense that it's greater than or equal to y sub m minus 1 over m. And then there's the complement, ones for which on day n the payoff is distinctly less than the payoff y on day m. But now n's getting bigger and bigger and bigger. And no matter what m you pick, it becomes fairly obvious that as n gets larger and larger, the set of omega for which the x payoff exceeds the y payoff gets bigger and bigger, while the complementary set approaches the empty set. Now we still have to take the contribution from the empty set into account, but since the probability of the empty set is necessarily 0, as long as we are talking about a bounded sequence of random variables, we can't get any finite contribution from that. We multiply 0 by the maximum possible value y sub n. Therefore, we can ignore the contribution from the complementary set, and what do we find? We find that the limit of n as n approaches infinity of the expectation of x sub m is greater than or equal to the limit as m approaches infinity of the expectation of y sub m minus 1 over m. And as m approaches infinity, the 1 over m term doesn't matter, and we conclude that the expectation of the x sequence is at least as great as the expectation of the y sequence. This argument would work equally well the other way around, so we can prove this inequality in the other direction, and we conclude that the expectation of x sub n has the same limit as the expectation of y sub n. This is a bizarre way to prove the result in this simple special case, but it turns out this is a proof strategy that is going to work quite generally for random variables that are not simple. And that's the conclusion of this little introductory talk.